So hi everyone, my name is Jie. I come in from the Adobe Systems Incorporated. I'm very happy that I can have a guest lecture here today. So today I will talk about using video viewing behaviors to detect the user's gender information. Here is an ad that I downloaded from Macy's.com. So this is very interesting actually. As you can see, the majority of the items are designed to attract female audiences or female customers. Actually, this is very common in online advertising because the gender information is a critical factor that every company cannot ignore in their business. So, why we want such information? Because with such information, we can target the desired customers. And this could greatly reduce the cost and also improve the return on investment. Among various demographic traits, gender information is a critical factor in precisely targeting the potential customers in online advertising. For example, like the companies makeup, skincare or makeup products will mainly focus on female audiences or female customers. The companies like razor producers like Philips will focus almost exclusively on male users. So this is very important to find the right customer when you do business. However, such personal information is usually unavailable to the digital media sellers. Why? Because the audiences may not register to watch the video, right? And number two, even for those who registered, they may not provide the correct information in registration. For example, when I register an account online, I just type some random information. So that's why the companies do not know the gender information or other demographic information of the users. So in this project, we propose to use the media consumption data to model the demographics to make the gender prediction. Why? Because different people may have different media preference. So we can use such information to build a model. And this model will greatly improve the accuracy than the random guesses. So to start our project, we sampled a lot of data from PPTV. PPTV is a Chinese online video platform, like the YouTube here. So we sampled 35,000, 70,000, and 78,000 users registered with ID cards in August, September, and October. The users registered with ID card is guaranteed to provide the correct information in registration. So we extracted all of their viewing records from the PPTV database. It contains more than 20 million viewing records in total. This table summarizes the number of users and the number of videos we sampled or we extracted from the database. One thing I need to mention here is that the female users account for approximately 25% of the total extracted users. So this is a very important baseline, 25%, that we need to keep in mind as we go forward. Now, based on the video tags that PPTV utilized to manage its video resources, we can group the videos into different categories, like the sports, games, movies, and so on. So we calculate the number of total views for each video and summarize the popularities of different video categories measured by the number of total views here. As we can see, some popular categories like TV series, animation, movies, and news account for more than 78% of the total views, while some less popular categories like sports, music account for only a small market and less than 3%. So what we want to know if there is any gender preference here. So we summarize the proportion of female users in each category. And you can see the sports and games demonstrate a very low proportion of female audiences. This is the baseline, 25% that we have in our population. And this one is 10%. So you can see the sports and games are more favored by the male audiences in China rather than the female users. And in contrast, the stars and entertainment variety shows show a higher proportion of female users than the baseline. Yeah, go ahead.
So let's say someone is both in games and sports. Are they extremely unlikely to be it, or is it the type of woman who watches sports and games videos is the same type of woman?
Yeah, for this one, we just summarize the number of users watch this video. Yeah, we do not say this one watch this only.
But my question was that if, let's say, someone watches a sports video,
yeah,
and then they also watch a games video,
yeah,
do they have, let's say, 0.001% chance of being 0.01% chance of being a woman, or is it still about 0.1 because it's?
I mean, because this is not independent. I mean.
But that's what I'm saying. How independent are they? That's what I'm trying to ask. Is how independent are those two things?
Because these things are calculated separately. So some user may watch this one and then watch this one. And some user may only watch this one, but not watch this one. So I mean, this is hard to compute exact value for this one. But you can estimate, right? So assume that this one is 10%, this one is 10%. So if these people watch these two videos, then what will be the possible range for this probability you can compute?
10 and 1%. Yeah.
Yeah, like this. Yeah. Okay. Okay. So for the female audiences, they also pay close attention to the daily lives and children. So one thing I need to point out here is that the categories like sports and games only account for a small percentage of total views, but they show gender preference. In other words, such kind of videos is more important when we try to predict the gender information. Because not all the people like this video, just a small group of people. Okay. So we also want to know if there is any gender preference for each video, each individual video. Of course, some videos are equally popular among female and male users, a lot of such videos. And, but also quite a few videos are more likely to be watched by female than male, or vice versa. So as we can see here, we will show it later. So to detect the videos with significant gender preference, we performed the Fisher's exact test to check whether the proportion of female audiences among the people who watched the video is significantly different from the people who didn't watch it. Then we find the significant videos because this is a multiple testing problem because we repeatedly tested. So we adjust the p-values with FDR or Bufferoni adjustment. Then the videos with adjusted p-value less than 0.05 are reported as significant videos. We say there is a significant difference in the people who watched the video and the people who didn't watch the video. And we also computed the odds ratio for each significant videos. So the odds is defined as the number of female audiences divided by the number of male audiences. And then the ratio is just the ratio of the odds from the people who viewed the video and the people who didn't view the video. So any questions? Yeah.
You're doing it for each type of video or each category?
Each video. Each single video.
Each individual video.
Yeah, each individual video. So this one is the category level summarization. And this one is each video, yeah. Okay. Yeah. So this table summarizes number of significant videos after the p-value adjustment for each odds ratio interval. So it is interesting there are a lot of videos that are still significant after we adjust it. And one thing I need to mention here is like August, September, and October, you can see the significant videos become larger and larger. Why? This is because the data we sampled here, we sample more data in September and August, October. When we get the data from August, we analyze it, and then we find that more data is better actually. So we ask them to give us more data. So with more data, it is more likely to be a significant video. So this is
Can the same video be watched during August, September, and October?
Sorry.
Can the same video be watched over the 3 months?
Good question. Yeah, that's true. Yeah, that's
Then
we will
how does that
discuss
show up
later.
in the tables?
So in each month, we will test it individually. So if this video is watched in October and this is significant, we count one here. If this video watched in September and it is significant again, then we count one here. If it is not significant, then we do not count here.
So is there any reason why you would do that by month, not look over the 3-month period and just in one grouping?
The thing is that because like different videos, for example, like the news, when it's uploaded, many people will watch this video. So the number of views is enough. Then we can find that this is significant. But later, the number of views will be greatly reduced. So it will not significant again. So it has different patterns in the video viewing behaviors. So that's why we do not put them together and summarize it.
No, you can still put it in one 3-month category.
3 months category and
Well, why do you care about the individual months? In other words, are you going to forecast just for people in August? You care about people in the future, don't you?
yeah, we predict the people in the future. Yeah.
Yeah. So I don't know. I mean, maybe you have a seasonality effect that you want to keep, but otherwise, I would think just over the entire span of the time you have more data, you have better testing.
Yeah, that's
data, more significance.
Yeah, that's right. When we do the experiments, we actually connect them together. So this is not a separate.
Just for showing us. Okay.
Yeah. Okay. Sorry. Okay. Yeah. So here, the odds ratio less than 1 means the proportion of female users among the people who watched the video is smaller than the proportion of female users among the people who didn't watch it. So this is a little bit long sentence, but so you can see if the odds ratio less than 1, it means the proportion of female users in the people who watched the video is smaller. And if this one is bigger than 1, it means the proportion of female users in the population that who watched the video is higher than the people who didn't watch it. And why we do not have the odds ratio equal 1 here? Because if the odds ratio equal 1, it means no difference with the baseline. So in the test will not be significant. So that's why, so that's why we do not. And the odds ratio bigger than 3, it means the number of female users is larger than the number of male users. So the number is larger. Why? Because the baseline is 25%. And based on this odds ratio computation, if this is larger than 3, then it means the number is larger. So this is very important because you can see the population, the female users only account for 25%. But now, for this video, more female users watch this video. Okay. Okay, let's talk about the challenges for this problem. The first one, the video viewing data can change along the time. The first one is the number of views can change. And the second one is the gender distribution can change. For example, a movie is released today. So today there will be a population, and tomorrow is another population. So as the time goes on, the people will change. For example, a famous movie just released today, everyone will watch it. But after several months, only the people really like it will watch it. Oh, yeah.
So, I guess I'm asking a version of the question before. You broke it down by month, but But now it looks like the key question you're looking at is really new releases versus older releases. How is that reflected in the breaking down by month? In other words, what was a new movie in month number I would probably be an old movie in I+2. And what are you really capturing with the month, breaking it down by month?
Because the data are collected actually weekly, so this data is not collected real time, so the historical data. Yeah, of course, we can summarize it as a whole data. Yeah. So based on this, we observed that a large proportion of the significant videos become non-significant in the next month. We do not say this is non-significant in the next month. We just say as the time goes on, the movie or the video becomes non-significant. And also, we also observe that some videos can maintain a long-term significance. So why it like this? The reason is that the continuous of emergence new videos. So every day the videos will be uploaded. So people will sometimes focus on the new videos. And also this is the video recommendation system that, for example, this system will today recommend this video, next day recommend the other videos, and so on and so forth. It will, cause the data changes. And also the property or the quality of the video. Like TV dramas and news are very different. Like news is actually a short-term video, and the dramas actually can be a long-term video. So the audiences watching the video may have some specific habits like binge watch. So all these things can be some reason for such pattern.
How would the video recommendation system, like how YouTube gives you recommended videos, how would that affect how 1 month there would be more women and then the next month there'll be more men watching the video?
Not like this, but it will affect the number of views.
Okay, but didn't we observe that 1 month more women will watch it than the next month, and then the next month more men will be watching the video? Isn't that what the second line is saying? I might be wrong.
I do observe, for example, like the news or the other things, the recommendation system could greatly affect the number of views. But for this one, for the distribution change, it mainly focuses on the TV dramas.
But isn't it?
Because as the time goes on, it can change a little bit.
But we're not just talking about the number of views, we're talking about specifically the proportion of men versus women views, right?
Yeah.
So that this recommendation system knows that it's giving these recommendations to women specifically 1 month and then...
No. Because if this system is, together with the PPTV website, if this system knows the gender, they do not need to predict it. Yeah, this just recommended the videos to people. Yeah. So these reasons, because of these reasons, so sometimes the data is changing gradually or dramatically. Yeah. Okay, so based on above observations, we denote the videos with short-term popularity as ordinary videos and the ones with long-term popularity as some classic videos. So the ordinary videos include the sports, news, and so on. And the classic videos include the TV series, movies, and we treat the videos as discriminate features and predict the genders based on whether or not they watch the video and the number of times they watch it. So because our data are collected in successive time intervals, here we formulate it as a multitask learning problem. So the model trained with old data or historical data collected at each time interval as related multiple tasks. For these long-term popularity videos, we treat them as short videos, short features, because this video will appear here, and appear many times. And for the news, like short-term videos, we say it is task-specific features. So it is usually locally belong to a specific time interval. And then in the next time interval, it will have very small amount of number of views. So for the short features, we will jointly estimate the coefficients across different tasks. For the task-specific features, we use L1 regularization to estimate the coefficients. So we can maintain an element-wise sparsity for the task-specific features. And for the short features, we can maintain a group-wise sparsity. The intuition is that if this video is important in one task, we have enough reason to keep this in the following tasks. Because sometimes the number of views may greatly reduce. So it does not mean that there is no general preference in this video. It's just not that significant. And the reason that why we do not put all the data together and train a model. So why? The first one is here you can see a lot of short-term videos only locally belong to some interval. Then we put them together. We'll inevitably introduce a lot of non-related videos because here this is the most current time and we want to predict the future user. We include the videos here and these videos will not be viewed by the people later. So that's why these inevitably include a lot of unrelated features. So ideally, if our method is, powerful enough, these features can be ignored because in the model training, if we do the feature selection and these can be ignored. But this is an ideal situation. So computationally speaking, adding these features will, decrease the performance. Not only increase the computational time, but also decrease the performance. So another reason that why we do not put them together is because, as we told before, the gender distribution will change along the time. So if we put them together, this distribution or this gender proportion is not exactly the one here. It is overall or the average. So we putting them together will, get some, get some data that is not, good enough to reflect our most recent situation. But if we use such method, things will become different. Why? For this one, the task-specific features, we do not jointly estimate them. So we can use L1 regularization and do the feature selection automatically during model training. So these things will not affect the things here. And for the short features, we use the group lasso penalty. Then the good thing is that we only say this feature is important, but we do not assume or we do not require that the coefficients should be exactly the same for every task. So yeah, so that's the idea. So any question?
It still seems to me that the key question is how independent different people watch the different videos are. We have a lot of data about each person.
Yeah.
So if the data is very independent from each other, then we'll know very accurately whether this person's a man or woman based on their large data set. But if we basically only have one piece of information, like the data depends on each other mostly, then we won't really know much. We'll know at most, we'll have a 50, 60% chance this person's, well, like a 70% chance this person's a woman. So
Yeah.
which one did you find it fit better with? Was it that it was a lot, you had a lot of information with each person, or you didn't?
Here we treat the video as a feature.
Right.
So we have a lot of videos and we have a lot of
And the
features.
were independent from each other. They
Yeah,
weren't-
that's right.
Okay.
Yeah, because in traditional classification problem, we do not assume that the features are independent actually. Yeah. Yeah, so the one thing here, as you mentioned, it is very hard to get very accurate results if you try to labeling all the users, because the data is here, and we only have such kind of data. So with noise data, you cannot, get a very high precision results. Yeah. So that's what we need to address also. So this one is our objective function. The first term is negative log likelihood, like the logistic regression. And the second term is L1, L2 penalty, or the group L2 penalty for the short feature coefficients. And the third term is L1 penalty for the task-specific features. Okay, yeah. So putting them together, we have this objective function. Just to summarize, we introduced the L1, L2 norm for globally and select and estimate the short features. And we use L1 norm to obtain the element-wise sparsity in the task-specific features. And because, as you can see, this one is convex, convex, and convex. So putting that together, this is convex. This will give us the global optimal value. And then this comes to the another challenge that we want to address in. Yeah.
Okay, you're not saying it's unique. You're saying it's you get an optimal solution. You're not saying it's a unique solution, are you? This L1 regression is not unique.
Oh yeah, that's right. Yeah, the global optimal. Yeah.
So not unique.
Yeah, not unique. Sorry. Okay, so this one. L1. Okay. Yeah. So here, we want to get high precision records because for this company, when you sell the advertisements positions to the other companies, you need to guarantee that you meet their requirements, meet the contracts in China. So for example, they want some company wants that 70% of my advertisements should be showed to some female users or to some male users. So this is written in the contract. And they will, ask third-party agencies to monitor this. So this is very important. We need to get a very good precision. Maybe not like 90% or 99%, but we need to get like 70% like this. So that's, or 60% at least. So this is written in the contract. So how to get this? Because the data is very noisy. If you labeling all the users, there is no way you can get this result. So here we formulate it as two detection problems, the female detection and the male detection. The basic idea is we label the users only when we are confident. If the users have enough data and enough evidence support this, then we label this user. Otherwise, we currently mark it as indecision, and we will label it later if we have more data. So we do not label all the users. We just label the ones that we are confident. And this is the decision procedures. Okay, so in the experiments, we will compare different methods. The first one is naive Bayes method. The second one is the logistic regression with L1 penalty. And the third one is the feature selection plus the naive Bayes classifier. The why? Because our method and the logistic regression with L1 penalty can do the feature selection automatically. So we add a feature selection for the naive Bayes to make them a good comparison. And why we compare with the logistic regression? Here, if we treat all the features as task-specific features, then this will reduce to the logistic regression with L1 penalty. Right? This will, because we just remove this one, put all the L1 penalty, then it will be the same. Okay, so we use three metrics to evaluate the method. The first one is the area under the ROC curve, AUC. The second one is the precision at K and the recall at K for the identified top K female users. Why we use female users? Because female users only account for 25% of the total users. So this is more important for us to detect, and actually this is more difficult for us to detect. And the third metric is the sensitivity at a nominal FDR level alpha. So in this metric, we want to answer two questions. The first one is, can we have a FDR level controlled, or can we control the error? The second question is, when we control the error, how powerful our model is. So for our proposed method, we can jointly train multiple tasks. So this is natural for our model to use historical data collected at different time intervals. But for the other methods, there is no single preferred way. So we try different strategies. The first one is we use only the most recent data only. The second one, we use all the historical data we have, and we put them together, train a model. The third one is we use the most recent data and half of the historical data. So we put them together and train it. This table shows the number of testing users in each experiment. We randomly repeat 9 experiments from August to October. We randomly pick a time and do the experiment. So add them together, there are like 70,000 testing users. And these users are also registered with ID cards. We hold it out. Yeah, so no overlap. Okay, this table shows the results for the metric 1. I want to make a few notes here. The first one is we can see the method with S1, strategy 1, is better than the method with other strategies. This is consistent from the naive Bayes logistic regression. So this is, as I mentioned earlier, this is because the data is changing, and you putting them together, you not only include many unrelated features, unrelated data, you also make things difficult and degrade the performance because the features is also changing. So it will also affect the coefficients, and then the performance is not, not increased. And the second term is the logistic regression with L1 penalty is usually better than the naive Bayes method. So this is in most cases. And our method is a little bit better than a logistic regression with L1 penalty. So this is expected. Why? Because we do not expect a big improve, actually, because you can see the benefits we have here is just from the short features. We just expect like 1% or 2% improvement in the AUC is actually good enough. Otherwise, it cannot be the case. And the improvement comes if the most recent data have enough data, then we do not need to use this one, right? So the improvements actually comes from here because this data is not that rich. And for the metric 2, we first order the users, testing users, based on the posterior probabilities, and then report the top K users as female users. And then we calculate the precision and the recall based on it. So here we only consider the strategy 1 because you can see the strategy 2 or 3 is not good, so we do not further discuss it. And then we can see our method is better, than other competing methods. Okay, so for metric 3, this figure shows the histogram of the posterior probabilities for the testing users. And you can see the different methods demonstrate very different shape. You can see the Bayes method, the naive Bayes method, tends to push the posterior probabilities towards 0 and 1. So it usually overestimates the posterior probabilities. So why? Because it makes some assumption. the assumption that features are independent from each other, which is usually not the case. And for other methods, the histogram is more reasonable. So that's why as we also do it in the experiment, this one cannot control any error because it is hard to find a cutoff to classify them because a lot of posterior probabilities will be 0.0 something, 0.00 something, so it is hard to classify them accurately. And now, then in the experiment, we set our nominal FDR level equal to 0.3, and we report the real experimental FDR level here. You can see it is a little scattered around the 0.3, but it is fine here. So we say this one can control this FDR rate. And we also do the experiments for other FDR level and also do it in the male users, because male users account for 75% of the users. So if you want to control 0.3, it doesn't make any sense. It will report all the customers as male users. So like this, yeah. So we also check the sensitivity of the competing methods at the nominal FDR level 0.3 for different experiments. We can see the number here is larger than the logistic regression. It is consistent a little bit better than that one. And if you use this one minus this one and divide it by this one, so you can see the improvement. So on average, it can get some improvements like 7%. Yeah.
Sorry.
Yeah.
That's a good question. So your response variable is female or male, right?
Yeah.
And the protected variables are the individual videos?
Yeah.
So how many videos are there in the sample?
Many videos, yeah.
Many more than the number of people that you're looking at, correct?
No, we have more people.
You have more people here?
Yeah, we have more people. As you can see, wait for a minute. This one, you can see. We have a lot of people. Yeah.
You have 377,000 videos in October.
Because we do not use all the videos. We only use the
ones that are
we do a pre-processing because this amount of videos is a large number, and a lot of videos will not be viewed by many people. Yeah. So that's why I say we will not use all the videos. Yeah.
And maybe related to the question you was asking, do you look at any interactions?
Interactions between the videos?
Yeah.
Currently, for this classification method, I do not further investigate the interactions between videos.
Even first order interactions, you don't think you would consider at all?
Because if you include the first order interaction, the number of features will greatly increased.
I agree, but you could still select some of them.
Yeah, that's right.
Main effects and just take the best.
Yeah, that's right.
The interactions that probably would give you a much better performance.
Yeah, that's right. That's right. Yeah, that's right. Yeah, that's right. I think we can try this later. Yeah, because currently the PPTV use this method in their system. So, and this is not that complex. So it is fine. Yeah. If we introduce more features, yeah, maybe we can try. Yeah. Okay, so for this project, the future work lies in the following directions. The first one is including different information like video tag, title, description, and reviews. The reason that's why we do not use this information is because such information is really, this is a really mess. So different videos may have very different, the title, description can be incomplete, or it is it needs to take some time to get them work. So, and another one is to predict the different demographics like age, education, income, and so on. Yeah. And also we can apply some method to overcome the sparsity problem, because many videos only viewed by very small amount of audiences.
You say small, but how many, what is small?
For example, some video only viewed by 1 people or 10 people. Some videos may never viewed by anyone.
And so you operate on the entire data set, you do not throw those out.
I throw that out.
Oh, okay.
Yeah, I filter that out. Yeah.
So you're talking about, time and how things can change over time. Are you using as a potential variable as how, when the content was created compared to how long it's currently, available to the public? Because that might be also a good way of keeping track as to whether or not the distribution will change.
Yeah, that's a good question. Yeah. So in this project, we do track some videos, and we do observe that there is a change as the time goes on. But we only pick some video that we think this will have a change in the time. So we find this one.
So one of the variables you could think about in this sort of meta-analysis could be, meta-analysis is how long. I'm assuming the videos embedded in that would be when it was created, or when it was posted originally. I'm not sure. I think it might be. If it is, you probably can use that information to study, so to speak, to what effect there'll be a change in distribution by just seeing how long it's out there.
Yeah, that's right. That's right. Yeah, that's a good idea. Yeah.
Okay, any last questions for Dr. Zhang? No? Okay, thank you very much.
So thank you for coming.